So many people think that we have to dig up archaeological sites, go through the jungle, and find an amazing monument or create something crazy like the Mandalorian in order to go back in time and understand our past. However, we don't really need that. We just need a $10 billion rocket and mirror to help us look back into our past and into the universe. So my presentation is on the James Webb, which was about $10 billion, and how it uses the light rays and mirrors in order to help us understand the universe and look back into our own planetary past, as well as the universe. So here are some images that the James Webb has given us, like the new Southern Ring Nebula, and then the new image of Uranus. And then in the middle here is a comparison between the Hubble telescope and the James Webb telescope of the Phantom Galaxy. As you can see, there's more definition, a little less blur, a little less cloud in the James Webb image compared to the Hubble image. So how does it work? It works by using the reflection of light rays, of course. However, it collects these distant galaxies and these dimmer light rays through infrared radiation, and it helps permeate dust, clouds. It helps collect these further dimmer images, which Hubble telescope cannot because it's more of an optical collection of light rather than infrared. And the James Webb also collects this information through mirrors, and it uses these multiple mirrors of convex, concave, and flat mirrors to help refine, remove, or lower the amount of optical um, distortions. However, we don't really need this $10 billion telescope to help us see distant galaxies. We have the Andromeda Galaxy, which is circled in the center here by the Milky Way galaxy, which we can also see depending on light pollution and where you are on Earth. But the Andromeda Galaxy is about 2.5 million light years away. However, there are galaxies and stars that are more than 2.5 million years away, which is why it's harder for us to locate and see with the naked eye. So how do we capture this light? Of course, the smaller our telescopes are, the less light that we're going to collect. The larger our telescopes are, the more light we're going to collect. However, even though if we make the largest telescope on Earth, it will still not collect as much information compared to the James Webb due to the atmosphere. And I have a little video demonstrating why.
So I'm going to use this cup that demonstrates a telescope, and then these pom-poms to demonstrate the light rays that come from distant stars and galaxies. So when we drop the pom-pom, the amount of pom-poms that land into the cup, or the amount of light rays that land into the telescope, are limited due to its size. So the best way to capture more light, of course, is by big, huge telescopes like the James Webb. And this is our little James Webb demonstration. However, another thing that kind of limits what we can do on Earth, which is why we create these huge telescopes, is our atmosphere. So, because we have an atmosphere, I created a makeshift atmosphere that blocks these light rays from traveling into our telescopes. So, of course, when dropping light rays or these pom-poms into the telescope, it doesn't catch too many, as the atmosphere stops it, as well as the limited circumference or diameter of the telescope. So that's of course why we have larger telescopes, like the telescopes of observatories, like the LA Observatory, as well as the other ones in Arizona. And those bigger ones, of course, can catch way more light rays than these smaller telescopes. However, when we shoot up huge telescopes like the James Webb over our atmosphere, it causes this barrier to disappear. So now, this is why the James Webb, compared to the Hubble, which is on the back side of this cup, the James Webb surely can capture a lot more light rays from distant stars that are unable to be captured by the Hubble telescope.
Now, when it comes to capturing these light rays, we can break down the telescope. Um, so we have about four different types of mirrors, um, counting the 18 segmented mirrors to be one, which is the primary mirror. That is our concave primary mirror, which then reflects to this focal point or the secondary mirror. The second convex mirror then shoots its reflected light into that protruding rectangular-ish object in the center of the primary mirror. That contains the tertiary mirror, which then reflects back into the fine steering mirror, which then shoots into the instruments located on the backside of the primary mirror. These instruments are called the Integrated Science Instrument Module, sorry. And so in this diagram to the left, it better illustrates what the ISM looks like, and how how the curvature is on the primary mirror, which then reflects into the convex mirror, which you can definitely see better on the left diagram. And then you cannot see the second and third, or no, third and fourth mirrors, apologies. However, I like the diagram on the right because it shows that each of these 18 segmented mirrors adjust in their own way to allow for more alignment towards the secondary mirror. So in that image to the right, it is an unaligned mirror, and eventually each segment is adjusted about 50 nanometers in order to perfectly align and reflect into the secondary mirror. And this big thing on the bottom of the James Webb, so you can see here as well, the bottom thing, are all just heat reflectance, and they keep from the sun, from the Earth, and other close by planets from having their own infrared rays be sent to the James Webb, which can disrupt these images. And so, what we've learned from the James Webb are some amazing things through these images. So, through the images, we can see how far and how old galaxies are, how fast these galaxies are producing stars, and what materials and elements are on these planets. So, through what the images are reading, through the colors that the scientists are seeing, they are able to read these objects and their mass and what their temperature is and what their chemical composition is. So it's really amazing things, and how we can better understand our universe, what created the planet, what created these distant stars, and what galaxies are more likely to produce stars and which galaxies are slower at producing stars. So these are my references, and that is the end of my presentation.